Welcome to the Aspen Center for Physics Public Lecture Series. The Aspen Center for Physics was founded in 1961 by local physicist George Stranahan with Michael Cohen and Bob Craig. The center provides a serene environment in which almost 1,000 prestigious physicists from around the world, young postdocs just out of graduate school to Nobel laureates, come together during winter and summer sessions to share, discuss, and initiate new research.
It took only 2 days at the center before I realized that this was what I had always dreamed doing science would be like. The beauty and peacefulness of the center is a really important asset to us. It is our opportunity to be cut off just enough from the daily grind to have lively discussions at the blackboards, share meals out on the lawn, gaze at the surrounding hills, and actually think about physics.
Thinking initiated at the Aspen Center for Physics, from biophysics to neutrinos to the outer reaches of the universe, has provided the underlying logic for the MRI, the CAT scan, and laptop computers, and will in the future provide the logic for innovations that will transform human endeavors.
So good evening, and welcome to the Maggie and Nick DeWolf 25th anniversary of the Free Winter Physics Lectures. I hope you enjoyed that film as much as I did. My name is Karen Rabe, and I'm a professor of physics at Rutgers, the State University of New Jersey. I've been a general member of the Aspen Center for Physics since 1995, and I'm also one of the organizers of the conference there this week, titled Advances in the Fundamental Physics of Ferroelectrics and Related Materials. Now, while only a few of you may already know what's a ferroelectric, nearly all of you have one in the pocket of your ski jacket. The memory chip in your lift ticket is based on a ferroelectric material. Hopefully, for another example, nobody in the audience has recently needed a medical ultrasound machine, but those work off the ability of ferroelectric materials to convert between sound and electrical signals. The design and discovery of ever better future generations of materials and devices is based on advances in the understanding of their fundamental physics now, and over 100 experimental and theoretical physicists from around the world are here this week to discuss the latest ideas in this field, stimulated by the natural beauty and the intellectual atmosphere of this unique place. Before we go on, I'd like to remind you that the next lecture of the series will be Exploring the Cosmos from the Moon. That lecture will be given by Jack Burns of the University of Colorado on February 10th, 1 week from today. And there'll be one more final lecture on February 17th. Our speaker tonight is not Jack Burns, as was erroneously published in the newspaper, but is Professor Jeremy Levy of the University of Pittsburgh. Jeremy is a graduate of Harvard University. He did his PhD in physics at the University of California at Santa Barbara, and he joined the faculty at the University of Pittsburgh in 1996, where he's received awards not only for research, but also for his excellent teaching. He's written over 75 published papers on topics ranging from quantum computation to spintronics to oxide nanoelectronics, and that last one is the basis of tonight's lecture, Etch-a-Sketch Nanoelectronics. Without further ado, it's my pleasure now to join you in welcoming Professor Jeremy Levy.
Well, thank you, Karen, and to all of the other organizers who made this workshop happen and allowed me to be able to come to Aspen. Otherwise, I would not have the opportunity. I'm going to try and tell you about some contemporary research that we've been doing the last few years. It's in this general area of oxides, and I'm going to try to explain a little bit about what we are doing and what we are talking about this week, and then I'll focus on the topic of Etch-a-Sketch Nanoelectronics. So this is a brief outline. Basically, I'm going to try to introduce this field in which we are thinking about this week, ferroelectrics, and especially in the context of information, ferroelectrics that can store information, and also give it some context in terms of the universe. And then I want to talk about the main topic, which is Etch-a-Sketch Nanoelectronics, and that will take up most of the talk. And then toward the end, I will talk about things that we haven't done, but we're very interested in doing with these particular materials, these systems, and particularly exploiting and controlling quantum mechanics at the nanoscale. So let me begin by trying to explain some of the words in the title of this program that we have been participating in this week. And I must say that I know there are some people who are from the workshop, and I'm not talking to you, so don't worry. If I'm making you cringe, then keep it to yourself. So basically, what I want to try to do is tell you a little bit about what ferroelectrics are, although my focus will be on the related materials. And then I want to say a little bit of what they can be used for. Like I think Karen basically explained it, but maybe I have some pictures. And then I want to also try to give some context of what is fundamental about this. So how is this an example of something that is fundamental in physics? So again, there's going to be a unifying concept in this talk, I think, which is a concept of information. So what is information? Well, I think we all live in the information age, and we all have computers or iPods or whatever, iPhones. So basically, information, digital information in particular, is stored as sequences of bits. So these are things that are either in a 1 state or a 0 state. So you can store your pictures, movies, etc., in a computer. But information is physical. So this is a mantra that was repeated over and over by a very famous physicist, Rolf Landauer. And what he meant by this is that you cannot separate the concept of information from the physical manifestation. And so all of information is stored in physical systems. And so we think about a bit, the fundamental unit of information, being one of two possible states, which we tend to call 1 and 0, that we can have various physical manifestations. So for example, the head and the tail of a coin, that's a bit. Of course, it's a very expensive bit. We can also think about thumbs up, thumbs down, right? Anything, basically 2 states, the wrist turned 180 degrees, right? That's one of 2 possible physical states that can store information. A piece of paper, you pick a particular location on that paper. The presence or absence of graphite at that location is a 1 or a 0. Now, we tend to use smaller things that are basically related to more fundamental properties of matter. So, for example, the north and south poles of a magnet, or the charge, basically positive and negative charges, the distribution of positive and negative charges. They can also be used to store information, and they do. Well, okay, so there's also, of course, a biological example, our DNA. They're one of 4 possible base pairs, and so that's 2 times 2, so there are 2 bits per base pair. They're about 3 billion, so you have basically your own flash drive, flash memory in your body. So information is everywhere. Basically, the configuration of matter is a type of information. So what are the best bits of today? So it sounds like a radio station. Basically, they come from the electric and magnetic fields or charges. And they generally tend to range from being very fast and volatile, like the memory in your computer. So the memory that's directly accessed by the computer is dynamic, which means that if you turn off the power, it goes away. But it's very fast. So then you have something like flash memory, which is a little bit slower, a little bit more expensive, but it has the advantage that when you turn off the power, you can still keep that information. So it's non-volatile. And then we have magnetic storage, so your hard drives. They are also slower, and they are still cheaper than flash memory. And they are non-volatile in the sense that the magnetic orientations don't change when you turn off the power. Well, okay, so I'm of course ignoring other things like optical drives and so forth, and I'm ignoring ferroelectric random access memory. But basically, what is it about information that allows you about physical systems that allow you to store information? Well, it's very related, very strongly related to symmetry. So, and symmetry breaking. So what do I mean? So here's an example. I have a circle. A circle is highly symmetric. You rotate a circle and it still looks like the same circle. So this is actually a very high symmetry state in which you cannot store information. There's only one state. But if you imagine now distorting this into an ellipse, for example, in one direction, then we have now two possible states. If the ellipse is longer in the vertical direction, we can call that a 0, or we can rotate it 90 degrees, and we can call that the 1 state. So now we have reduced the symmetry. An ellipse has lower symmetry than a circle, and because of that, we can store information. So this could store a bit, for example. Of course, I don't know what this is. Maybe it's an egg. Well, there are lots of examples, of course, in nature, and one local favorite probably is water. And so water is the high symmetry state. This is like the circle. But what happens is when you cool this water down, there is a transformation, and of course it turns into snowflakes. And we all know that no two snowflakes are alike. And so there's a very rich behavior that happens when there's a transformation, a phase transformation from this spherical drop of water into the many different types of snowflakes that can form. So with a lowering of symmetry, now it's six-fold instead of around a boring drop. This is where information occurs. Now, once having information is not sufficient. So if you have a computer, inside at the center of that computer is the central processing unit. That's where all the information is processed. And without that, you just have storage. You just have a flash drive, but it can't do anything. It can't play your movies, for example. You need something like logic. So you need to be able to change the state of information based on prior information. And this is done actually with a great variety of ways of storing information. There's really basically only one way of processing, and this is done using control over electricity. So this is basically it's what's called a field effect transistor. It's a switch, just like on and off switch, except that it's much smaller. So the idea is that you have here a channel. Well, in fact, this is the off state. So in the middle, you basically have prevented electrons from flowing from one side to the other, but you can apply, you can put positive charges on the top here, and they attract the negatively charged electrons, and now you've closed the switch and electrons can flow. So this is an on-off switch that allows you to control the flow of a current. So with a field effect transistor, you can make a logic gate. So a logic gate is something that actually does exactly what we need for computation. So in this case, we're taking 4 of these transistors, hooking them up, and now we have the ability to compute the output, a logical consequence of the inputs. So the 2 inputs are now either in a low L or a high H state, and only when both of them are high is the output low. Otherwise, the output is high. And so this is what is called a NOT AND or a NAND gate. And it turns out, I picked this one because it turns out that all of the possible programs, everything that we do with computers is assembled from, can be assembled from a single type of gate like this. This is a building block for computing. And so it's very important, and the fact is that you can do it using physical systems. Well, so again, putting it into even greater context, information is everywhere in the universe, and in fact, these concepts of symmetry breaking also play a very important role. And I did notice that the last speaker was talking about the Large Hadron Collider, in which they were trying to find this Higgs field. So the Higgs field is like the sphere, and basically there's a transformation that takes place on the scale of the universe where that field turns into all three of the four forces that we know about: the electromagnetic force, the strong force, and the weak force. And so this kind of phase transformation accounts for all of the complexity in our universe. And that complexity is associated with information capacity. Now, there was a physicist who actually tried to push this analogy very far, and he said, well, okay, if the universe has information and maybe the laws of physics are the logic, how powerful is this computer? Well, it turns out, according to his calculations, there are 10 to the 90 bits of information in our known universe, and so far there have been 10 to the 120 logic operations performed on those 10 to the 90 bits. Well, okay, this is both a very large number, but it's not infinite. But it's a very interesting way of looking at the universe. Now, when I think about this for too long, I get into a certain mode, and
He's the one.
That's right. So the storage in my brain starts to replay the matrix. I had this matrix epiphany. So again, the idea is that the universe is really a computational engine, and it's computing our future. So another way of thinking about it is that we have the universe, which is in a certain memory state where everything is at a certain time, and the laws of physics are what take you from the past to the future, or actually from the future to the past. And so this is really, okay, it's just a movie, but really the analogy, I think, is a very powerful one and predated the movie. So again, really the goal of physics is to try to understand what are the laws of physics and what are the possible states of our universe. Okay, so now I want to tell you a little bit about ferroelectrics. I'm not going to talk too much about them because I'm really more interested in the related materials at the moment. But ferroelectrics are crystals, and they have this property that they can store information through the charge that is in their crystal structure. So they're not metals, so they actually have bound charge, but the distribution of that charge can be used to store information. It's very similar to the way in which magnetic hard drives store information. And in fact, that's where the name ferroelectric comes from. It's like magnetism, like ferromagnetism in iron, but they generally don't contain iron. Now, there's a very important concept in this, in all of solid-state physics, but in particular to understand how ferroelectrics work, and this is the concept of the unit cell. So again, we have these crystals, but they are made up of atoms ultimately, but those atoms are arranged in certain ways, and they're building blocks. So you could really think about, for example, a construction like a house made of Lego blocks, and really what we want to understand are what are the properties of those individual blocks, because if we understand the property of that single block, we can make larger structures and understand how the very big crystals behave. So these are called unit cells. This is one illustration of a unit cell containing the atoms in barium titanium oxide, or barium titanate. And so you have barium and titanium and oxygen atoms in a fixed arrangement, and then that arrangement is repeated over and over 100 million times in all directions, and that makes up a big crystal that you can hold in your hand. But they basically are made of atoms. So I want to focus on this barium titanate. In particular, this is like the sphere. So in its cubic phase, it actually has a lot of symmetry. So it's a cube, meaning that all of these sides, the length and the width and the height, are all the same. And this is actually a very high symmetry state, and in particular, it's one in which you cannot get ferroelectricity. So it's too highly symmetric in order to be ferroelectric. But in fact, you can cool it down just like cooling water into ice. And what happens is that this unit cell actually undergoes a structural transformation. So it begins to get longer along one direction, and other things happen as well. It turns out that there's a separation between the positively charged titanium ion in the middle and the negatively charged oxygen atoms. And so that actually has a separation of positive and negative charge that can be used to store information, because you can imagine turning the whole thing upside down now, and that's what it looks like upside down. So you flip the minus and the plus, just like the north and south of a magnet. And so this becomes the 0 and the 1 state, which can be used to store information. So it's very similar to the way we are interested in storing information in these ferroelectric materials in a very similar fashion to the way in which magnetic materials are already in your hard drives in computers. So magnetic domains or regions that have the same orientation are used to store information, in particular single bits, and they're quite small. This is just an image of how a hard drive works, a spinning platter, and then there's something that reads the magnetic properties. So these bits are very small, and so here actually you see a single human hair, which is about 80 microns, and in particular the magnetic domains are quite small by comparison, and so and they need to be small because you want to have a lot of capacity, so you can store all of your movies. So I say it's small, but it's not as small as ferroelectrics. So ferroelectric materials have the same kinds of structures, except that now they're really approaching the atomic scale. So what you see here on the right is, this is actually a real image. This is not a cartoon. These are the real atoms that you're seeing, the repeated unit cells of a material made from bismuth iron and oxygen, bismuth ferrite. So it turns out that actually I stole this from one of the talks this week, because this is a very hot topic right now. Because not only can you make these structures and have domains which are very small, but this particular system has the property that there's a strong coupling between electricity and magnetism. And that's a very interesting thing, that if you can actually control magnetism through electricity or vice versa, that's a very powerful way in which to control and process information. So we also have been working, my group have been working with ferroelectric materials. This is strontium titanate. And what we did in this image was we actually are able to color the surface of this material. This is strontium titanate, a very thin layer grown on silicon, the same silicon that's used in ordinary computers. And the strontium titanate can be polarized like ones and zeros, and that's what the red and the yellow represent. So this is actually a picture of strontium titanate unit cell on the unit cell of silicon. So this is strontium titanate on silicon on strontium titanate on silicon. So it's like the material is wearing a T-shirt, which is a picture of itself, kind of like Homer Simpson here. So I like these self-referential types of things. Karen mentioned some of the applications, and again, I think all of you, we have some skiers in the audience, right? So only a few? Right, well, you have all of us to thank, because without that, you wouldn't be able to go skiing. So these ferroelectric smart cards, I guess, are now being used. And the idea is that actually you have information that's stored in the ferroelectric state and read out through electromagnetic waves. And it's non-volatile, meaning you don't need batteries inside of these things for them to work. And again, ultrasound is another very powerful application of ferroelectrics. So this, remember I mentioned that there was this structural transition that occurs, and that movement actually can be used to generate sound, and that sound can be used to propagate through a body and get very high resolution images. This is a very powerful medical applications. But what I really want to talk about at this point are the related materials. So I've told you about some of the fundamental physics and ferroelectrics, and now it's time for the related materials. So the ferroelectrics are a part of a broader class of what are called complex oxides. So these are materials that contain oxygen, but have a more complicated structure than sand, for example, silicon dioxide. And so Of course, ferroelectricity is one of them, but actually some of magnetism is also another property of these some of these oxides. Some of the conducting materials are very sensitive to magnetic fields, and some of them have this ability to have their electrical resistance go completely to zero and become superconducting. So I want to talk about a very interesting, what's a so-called emergent phenomenon that occurs when you take two different materials and put them together. So usually, if you take an insulator and you have another insulator and you stick them together, you get two insulators stuck together. So it's more like, I guess you could say, if you take peanut butter and jelly and bread, you put them together and you get a sandwich, something that's different from all of the different constituents. Well, that happened in this particular system. So this is a system that consists of a very thin layer of one oxide, and that's lanthanum aluminate, lanthanum and aluminum and oxide, and then it's grown on a very thick layer of strontium titanate. And what was discovered about 6 years ago by Otomo and Huang was that even though separately these two materials do not conduct electricity, when you put them together, right at the interface between them, you can conduct electricity. It's a very interesting property. And in fact, it was later discovered that that transition from being an insulator to being a conductor depended on how many of these unit cells of this top material you had. And other properties like magnetism emerged, superconductivity. So it's a very interesting and rich system. I learned about this system when I was at a conference in Germany that was taking place exactly at the time of the World Cup. So it was in Germany, and I had begged my brother, my older brother, to obtain a ticket to the final, and he did, and he said, "That's going to cost you 4 birthdays." And I said, "That's fine." And the only problem was that there was a week time between the end of the conference and the final, and again, I can't afford to come to Aspen. I can't afford to spend a week in Germany on vacation. And so I ended up traveling throughout Germany and the Netherlands and gave talks in various places. And one of the places I went to was University of Augsburg, where they had discovered this very interesting metal insulator transition. And so again, we have a very thin layer of one material that's an insulator grown on a very thick layer of strontium titanate, the second material. They're both insulators. What they found was that, and they were able to vary the number of unit cells, so going from 0, 1, 2, etc. And what they found was that when you had fewer than 4 unit cells, this interface between the two materials does not conduct electricity, but above it, it does. So it's a metal. This interface is metallic above this 4 unit cells, and it's insulating below it. But even more interesting was that if you have exactly 3 unit cells, they discovered that they could actually switch that interface back and forth between the metallic state and the insulating state by applying a voltage. So they apply a positive voltage, and the interface becomes conducting. And they turn off the voltage, and it stays conducting. Then they make it negative, and it goes back to the insulating state. They turn off the voltage, and it stays in the insulating state. So I saw this, and I said, wow, it's a bit, right? Because insulating is 0, conducting is 1. That's a bit. And that's a really fascinating thing. So it also is a very interesting phase transition and so forth. But it also can store information. And so I was fascinated by it. I couldn't stop thinking about this. It basically ruined my World Cup. So I basically missed all the important things that were happening at the time. There I was in the corner asking, okay, is it possible to take this and make it smaller, to do a local version of this? Well, okay, long story short, now I'm sitting here talking to you. Okay, so it worked. And basically, what I had thought of immediately, pretty much immediately, was that this is very much like the toy that I played with as a child, Etch-a-Sketch. So people all know what Etch-a-Sketch is? Okay, well, if not, I brought one. I brought mine, okay? So I'm going to pass it around. If you're an expert, then please just quickly hand it off to the next person. And no profanity, so just... Right, so, well, an Etch-a-Sketch is a great device. It's a drawing tool, and you can make very elaborate drawings with it by turning these two knobs. What happens is the way that it works, if you rip one open, and please do not rip that one open, yes, I want that back at the end, is that it's basically an enclosure inside of which there's fine aluminum powder. And the top surface is glass, typically glass or some plastic, and the aluminum sticks to it naturally. And so when it sticks, it's basically reflective, and in fact, it's metallic. So, and that's one of the reasons why it reflects light. And then what you do is you move the knobs, and the knobs scrape off a small portion. So this point here is touching at some point, and then it scrapes as it moves and pushes away the aluminum powder, and then the light, when it hits the surface, it doesn't reflect, it goes inside, and it looks dark. So all the dark regions that you see here are where the aluminum has been moved away, and that's the insulating state. So this is actually milliscale control of the metal insulator transition. So that's fine, that's a toy. The other thing, of course, is that you can turn it upside down and shake it, and aluminum powder sticks again to the surface, and you've restored the initial state. So that's just a wonderful thing about it. Of course, if that property were not the case, I don't think it would have been as popular. Now, so that's a toy. In the lab, we work with tools. And you can see there's a big, big distinction between them. These tools, of course, cost about 10,000 times more than that one there. But they actually do very similar things. So we, instead of having a stylus that's maybe 1 millimeter in size, we have a very sharp point. This is made out of silicon that's on the order of maybe 10 nanometers, or basically 40 or 30 times the distance between atoms. So this thing can be used to move along a surface and figure out things about the materials. For example, the surface, the height, or other properties. And it can also be used to change the properties of the materials if it's conducting. So let me explain how we do this writing and erasing. So really what we're doing is essentially the same thing, except we're doing it at a local scale. So we're changing this interface from an insulating state to a conducting state by moving a scanning probe across the surface. So the green areas are going to represent conducting regions, and the red areas are the insulating regions. So the basic idea is we're going to scan with a positive bias applied to that probe, and when we do that, we flip locally the interface from the insulating state to the conducting state. And we can measure the result of the consequence of this by trying to flow electricity from the left-hand side to the right-hand side. And what we find is that when we move across and complete the circuit, we're suddenly able to flow current. So that's what's happening here. The current through this that we're measuring is jumping up. Well, that's fine. So now we've made a wire. We can also then do the equivalent, which is to erase it. So in that case, we apply a negative bias and move across, and that cuts the wire. Now, here was this really surprising thing. What we do is we're monitoring the current through this wire as we move the probe and try to cut it. And what we found is that it cuts over a very, very small distance. In fact, it's about 2 nanometers. So 2 nanometers is 5 unit cells. So it's really 5 times the distance between atoms. So what we're doing here is we're making structures, electronic structures, whose scale is approaching the distance between atoms. And the fact that it's reversible is also something that makes it especially interesting. Now, we are, of course, in the process still of investigating the mechanism, but we actually think that water plays a very important role. It turns out that these surfaces, again, these are models that are depicting where all the atoms are in this material. And here, this is one in which we have 3 unit cells of this lanthanum aluminate. And it turns out that water likes to stick to the surface of that lanthanum aluminate. And when it does, the surface actually rips those water molecules apart. And so there's a hydrogen over here and an oxygen, hydrogen over there. So it pulls them apart. And what we believe we're doing is with this probe is we're actually pulling off the oxygen and the hydrogen, and we're leaving a charge which is positive at the top surface. So that positive charge attracts electrons to the interface, but only directly below. And so we believe that that's how we change the interface between the insulating state and the conducting state. So then when we change, we erase by pulling off this hydrogen, and when we do that, we can restore the system to its initial state. So this allows us to go back and forth to locally write and to locally shake this Etch-a-Sketch system at the nanoscale. So again, the idea is that really what we have is a very material which acts like a dense array of transistors, non-volatile transistors, whose size is approaching the atomic scale. And so again, these are these positive charges which are attracting the electrons to the interface. Where there are no positive charges, electrons cannot go there. And so what we do is if we write in between, then now the electrons can flow. We have closed the switch. And then we can, if we remove those positive charges, then we open the switch. So it's a switch, but one that can be done, repeated over and over again. And this is very similar to what I had showed you before with this field effect transistor. So we have the gate off and the gate on. So this is this material is basically, it can store information, but it can also has the property that it can process information as well. So what are the possible applications of this? Well, one of them I think I sort of alluded to is that if we have the conducting state and the insulating state can be the 0 or the 1 of a memory device. And so by placing these dots on a surface, we can store information at very high density. And so actually we did an experiment to try to see how closely together we could place these individual dots. And what we found is we could vary the size and then basically place them a certain distance apart. And when they overlapped, then they would conduct from one side to the other. And what we found is that as we made them smaller and smaller, eventually we got to a point where it's about 1 nanometer. And that's a very small size for a memory device. Typically, it's about 1,000 times smaller than what is used right now in conventional devices. So another thing that we wanted to do was try to look at the properties of these electrons as they're flowing at the interface and confined in very narrow wires. And so I call this quantum mechanics on the fly because what we're in quantum mechanics, we have we think of electrons as being waves, and these waves can actually tunnel through barriers. And here, what we're going to do is we're going to create these designer barriers, and we're going to watch as the electrons move through or are blocked by those barriers. So here's the idea. We start with a wire, and what we're going to do is very gently erase. So we're not going to completely cut the wire, but rather we're going to just very gently start to remove those hydrogen ions and start to raise the barrier between electrons that are on one side and the other side. And the picture is that we have basically a tiny barrier, and the electrons, it's very easy for them to move across that tiny barrier. But basically, they all make it across. And the conductance, which is being plotted over here, is very high. So then we can write some more and increase the size of the barrier. And what we find is the conductance is reduced. So basically, that's because now we have a higher barrier. So now you can see that it's a little bit harder for the electrons to get past the barrier, but they can do it eventually. So we keep doing this. And, all right, so, okay, keep doing that. And eventually we get to the point where if electrons were classical, they were classical objects like us. So don't try this at home. You know, if you're going skiing, don't think that you can tunnel through that tree. You cannot, okay? But electrons can tunnel through this barrier. But if they were classical, then basically what we would expect to measure is a very, very small number of electrons that are actually passing from one side to the other. So it kind of looks like this. The electrons are trying. They just can't get over that barrier. Oh, look at that. Almost, but not quite. Okay. Right? But electrons are not classical. They're quantum mechanical. And what it means is that every once in a while, an electron will actually get through. It will go through the barrier. So this is a property of quantum mechanics, which is, of course, our whole universe is quantum mechanical. But here, we're able to play and observe the effects of quantum mechanics in a laboratory without too much effort. Okay. All right, so now I want to talk about the transistor. So I said this is a transistor-like material. Well, what I'm going to do is try to create something that more closely resembles the transistors that we use in computers. And so, well, okay, I have an acronym here. I like acronyms. So we call this a SketchFET. So I had to figure out what words to use that meant sketch. So sketch-based electronic transport within complex oxide heterostructure field effect transistor. Okay, fine. It's a SketchFET. But it's really important because transistor is the most important invention of the 20th century. It has transformed everything because all the computers, everything that we take for granted, all came from this single invention. So if you really want to have an impact, you've got to be able to make a transistor in terms of information technology. Now, this is how transistors are made today. So if you buy a state-of-the-art Pentium device that uses basically 45 nanometer scale structures, it's very complicated. So this is basically, you have many, many steps that are involved. So you have additive steps where you're incorporating new materials into silicon. You have subtractive steps where you're etching away, removing materials. And then you have transformative ones where you're converting one material of one form to one of another, like silicon to silicon dioxide. And this is a very complicated process. So by contrast, I want to show you how simple it is for us to make a transistor from this system. So all transistors are three-terminal devices. So basically, you have source and drain. So you imagine pouring current into a source and it exits in the drain. But then there's a gate which will impede the flow of the current. And so there are three terminals. And so the step one is we make a T-junction. That's the technical term. It looks like a T. And basically, we do that just to make our leads. And then we erase a small area in the middle that's 1 micrometer on a side, and we write our tiny wires, which are only 2 nanometers wide. Now, all during this time, we can actually measure the properties of the device. And so far, at this point, it's not a transistor. And so if I measure, actually, I see that, well, I'm not going to explain what this is, but this is not a transistor. Basically, it's not turning on and off as a function of that gate in the middle. So we need to modify this a little bit further. And what we're going to do is we're going to cut the wire in this channel. We're going to make it insulating. And then we're going to take this middle lead here and pull it back a little bit. And this acts like a transistor. So depending on the voltage that you apply to this gate, you can make current flow through this channel or not. So the blue curve is when 4 volts is applied to this gate, and you see that actually when you apply voltage, you get a current. So that means that this is conducting electricity. And then if you put negative voltage on the gate, then you can basically shut it off. So this is a switch. And but it's a very small one. It's the area of this is about 1,000 times smaller than the current state-of-the-art transistors. Well, okay, what is the bigger context? Again, we have a system which is, has the ability to store information in very high densities, and it also has the ability to process information as well. This is a picture of this, it's called Fab 32, and that's where you buy these state-of-the-art transistors. And basically, memory and logic, as I have told you, they basically are made from different systems. You have maybe magnetic storage, and then you have silicon processing. But here, we're able to make from the same systems a way of storing information and processing it on much smaller scales. So it could be that we, not only can we shrink the size of the elements used to store and process information, but in addition, we may be able to reduce the size of the device that is used to make the computing power to begin with. I mean, we're shrinking something that is the size of Fab 32, which is about 17 football fields in area, to the size of something that you can fit in your hand. Okay? And so that's about 10 orders of magnitude difference in size. That may sound very fanciful, and maybe there's some chuckles from my colleagues. But I want to point out that actually the technology for doing this already exists. This is something called, this is a movie taken from the IBM website. This is something called the Millipede project. Millipede, again, having 1,000 feet. In this case, we have 1,000 of these probes. In reality, they have already demonstrated 4,000 of these probes that are basically scanning over and doing something to a surface. But in fact, so again, they have done this onto something that's about 7 millimeters by 7 millimeters. So they can actually already fit 4,000 of these little tiny probes. They can read out information, et cetera. And I think basically the question is whether they can find the right medium. And it's, of course, an open question as to whether we can take this nanoelectronic material and integrate it with something like this Millipede probe-based storage and turn it into a storage and processing unit. Okay. Okay, so we basically may be able to not only have a way to store information with very high density, but also have a way to create circuitry as well. All right, so in the last brief part, I want to talk about things that I haven't done. And that's, of course, those are the things that I think about. All the stuff I've done is boring, and things that we haven't done is exciting. And I've been interested for a long time in something called quantum information. So I told you a lot, I've talked about information. And we know that information is stored in states of matter that can be in one of two states, like heads or tails, et cetera. Same is true, except that we know, for quantum information, but we know that the whole world, everything is ultimately quantum mechanical. And so the idea is that a quantum bit is a system that can be in one of two quantum states. And one of the things that we know about quantum mechanics is that if you can be in one state and you can be in another state, you can be in both states at the same time. This is what's called a quantum superposition. So think about Schrodinger's cat being alive and dead at the same time. It's basically a very similar thing. And the idea is that, of course, we're not interested in doing any harm to cats, but the point is that we don't mind taking very small, otherwise inanimate materials and examining and focusing in on their quantum properties and trying to exploit that for the purposes of computation. And so quantum information is also physical. This is David DiVincenzo is quoted here, and he was sort of paraphrasing Rolf Landauer. So as one example, I will give basically electron. Electron has a property that it has something called spin. So the electron can spin clockwise or it can spin counterclockwise. That's a way of thinking about it. But again, because it's quantum mechanical, the electron can spin both clockwise and counterclockwise at the same time. And that ability, that extra flexibility, translates into increased computational power. And that computational power is is truly immense. In fact, if you try to simulate 100 quantum bits, we don't have enough classical bits in the universe to do it. And we don't have enough computing power either. In all basically the time of the universe, we would not have been able to simulate what happens to 100 quantum bits. Okay. So one way in which you can imagine taking these spins is you can't just take an electron and just have it in vacuum. You have to put it somewhere. And one place that you can put it is in solid state materials like semiconductors. And this is a system made out of semiconductors, not the ones that I've been telling you about, where basically the green areas represent areas that electrons can be in, and these are places where the electrons are forbidden for being. And and it's possible to make them sufficiently small that you can put 1 or 2 electrons only in those boxes. And so this is an example of where they have a system which they can control 2 electrons and allow the spins to interact, which is a type of processing that can take place. And the idea is to use that natural physical processes to do computation. So basically, we would like to do something very similar to this, maybe shrink it down by a factor of 10 in both directions, and try to see if that can work even better. Another approach is something called quantum simulation. So it's a very different approach to quantum information, where you have a material like a superconductor. And here you can see a high temperature superconductor that's basically floating a magnet. And you want to understand what are the properties of that material. Well, it turns out that it's very easy to write down equations, but it's very hard to solve them. And one way is to actually try to simulate them. And so there's a community out there which is using optical lattices. So basically they are trapping atoms in the standing waves of light. And those atoms basically represent or solve the equations that correspond to various theories that relate to superconductors. Well, I'm interested in doing something very similar. So we want to be able to create two-dimensional networks of traps where we can hold individual electrons. And the spacing between these traps is small enough so that we believe that we can do this. And so we want to actually simulate the equations that are too hard to solve using ordinary computers because they involve quantum mechanics. So this is just I'm not going to explain any of this, but basically there's a whole bunch of stuff that we would like to do with these systems that are all quantum, things that require you to cool down to very low temperatures and explore interesting properties that have been seen in other materials. And so we're interested in exploring those as well. So I'd like to summarize at this point. I tried in the beginning to explain, I mean, of course, there are applications for all of these materials, but really there's a reason why we have fundamental physical interest in them. And I like to think of it in this context. So basically, computers as a model paradigm for understanding the universe, where bits, our states of matter can be used to store bits or can represent information and richness that we would like to understand. And the laws of physics are the things that allow them to transform in time. And so ferroelectric memory is a very nice example of a system that has a lot of richness to it, the polarization that can store information and be transformed in various ways. So as a related material, we were able to find a system which also had two states of matter, the insulating state and the conducting state. And what was very interesting is that this system not only can store information, but it can process it as well, and process it at densities that are approaching the atomic scale. And that's really the highest density in 2 dimensions that we can imagine. And there are many applications or ways in which we can take this power and turn it back on itself or back into useful applications to improve maybe the speed or the energy efficiency of ordinary computers, or to go beyond altogether and to create quantum computers which have properties that are truly magical and unattainable at this point. So thank you for your attention. Yeah. So I don't want to forget to acknowledge all of the people that I work with and who support this work. Chang Sen is a graduate student who actually got this Etch-a-Sketch thing to work for the first time. And it's a very rare thing because we try lots of things that don't work and we don't talk about them. And this is one thing that worked. And the problem is that if you know something's going to work, then you know that you can just keep trying. So she was able to get it to work, not knowing that it would work. And that's really, that's a big hurdle. Patrick Irvin and Daniela Bogren are also doing work with the Etch-a-Sketch. Materials, I don't make the materials. I collaborate with best people in the world who do, and Daryl Shlom, his postdoc, then postdoc, Maitri Warasawatana, and of course Jochen Manhart, who gave me the first sample that we tried this Etch-a-Sketch with, and his group, and Changbom Om, who's here, and of course also with theorists who think about why these properties exist in these materials, like Steve Helberg. And so the support comes from the various funding agencies, including the National Science Foundation, DARPA, Army Resarch Office, and Air Force. So again, we'll thank them.
Okay, so thank you very much, Jeremy. We have time for some variety of questions. Anybody? Yes.
The question is, you reduced your cell size, and what about switching speeds? Because we normally think when you reduce size, switching speeds increase. Maybe there be heat issues, power issues.
Right. So yeah. So maybe what you're asking. Yeah, I'm going to. So maybe what you're asking is, what are the downsides? So if you reduce the size of, let's say, a transistor, what are the effects on, let's say, the ability to transmit current and so forth? Again, it's hard to make a direct comparison because transistors are not made from these materials. But I should point out that the materials themselves, the electrons are less mobile in these materials than in silicon or in gallium arsenide. So that's, to begin with, they're actually moving much more slowly and dissipating more energy for the same amount of voltage. So exactly how the full benefit or cost in the end, how that works out is something that we don't know the answer to. Okay, so you said that in quantum mechanics things are random, and how do you come up with things that are not random? Well, it's true that if you let's say you are in a superposition of two states and you try to do a measurement, then there would be there's an essential element of randomness to it. So one of the things that you need to be able to do to make a quantum computer is you need to start in a well-defined state. And so you need, for example, to have all of your spins, electron spins, spinning clockwise. So that's very similar to what you do in an ordinary computer. You initialize, let's say, all of the memory to 0 state. So you do the same thing in a quantum computer, and then you want to do a quantum algorithm. So you're going to have all these interactions take place. And if you have chosen your algorithm correctly, then the probability of getting the right answer should be high, sufficiently high, but it won't necessarily be 100%. So in fact, even if you had a perfectly working quantum computer, you won't necessarily always get the correct answer. But it turns out, well, you might say that, well, then why? Why do you care? Well, okay, so let me, what?
We don't care now.
Well, I think it's a valid concern, right? This element of randomness, how does it influence the computation? So one of the things that a quantum computer can do is factor large numbers. So, well, to give an example with a small number, something I can factor is 15. 15 is 3 times 5. 3 and 5 are prime numbers. So it turns out that if you take a very large prime numbers and multiply them together, you get an even larger number. So let's say 200-digit number that's a prime number, and another one that's 200 digits long. You multiply them together, you get a 400-digit number. So it's very easy to multiply them together. Actually takes milliseconds for a computer to do that. To factor them, to separate them out, will take longer than the age of the universe for all of the known computers that we have. A quantum computer can factor numbers in a time that basically scales as a number of digits. So it's exponentially faster. And so if the quantum computer gives the wrong answer half the time, that's okay, because you just run it, you can easily check whether that answer was correct or not. So if the computer spits out, the quantum computer spits out the wrong answer because of quantum randomness, then you could say, oh, well, I know that's not correct, let me run it again. And the probability is maybe half the time it will do it. So if you run it enough times, it's a lot less than the age of the universe. So it works out that quantum computers can still get it wrong some of the time and still be so much faster than ordinary computers.
Okay. Keep it simple, thank you.
Yes, they do. So basically what we do is we write circuits, and they basically stay, if we just keep them in our atomic force microscope, they basically will leave after about a day. But if we put them in a sealed environment, they actually stay indefinitely, as far as we know.
So you have to have the hydrogen on top for them to stay?
Well, so what we do is that sealed environment is actually under modest vacuum. So we want, I think that plays an important role, but exactly what role it does play, we're not sure.
Doesn't this, to a large extent, really depend on a belief that the quantum activity is truly random and not subject to some bias we don't yet understand?
Well, so maybe the question is, in the context of quantum computing, does it rely on some assumptions about the randomness? I think what it relies on is a belief in quantum mechanics as the ruling law of the universe. And quantum mechanics is the best tested physical theory ever was. So we know a lot about quantum mechanics. It has been verified over and over, and it makes predictions that are statistical in many cases, but they are borne out through experiment, and they're very well tested. So I don't know whether a quantum computer will be able to, for example, do something that will bring us into a contradiction or conflict with the basic tenets of quantum mechanics. I doubt that they will.
So, yeah, sorry, let me throw in one question just to bring it back to a little more to the subject of the workshop, which is that maybe some people are wondering how the materials that you used in your Etch-a-Sketch are related to the ferroelectrics, because you said you're looking at related materials. And also, coming back to materials, what do you think about the prospects of improving the Etch-a-Sketch by playing around with some, other materials for the device?
Okay, Karen. So actually, I'm giving an invited talk, and everybody's invited. There'll be a more technical one on Friday, in which I actually use the Etch-a-Sketch and turn it around and use it as a probe of ferroelectricity in that strontium titanate layer. So strontium titanate was that big, thick layer, and the interface between the two which was actually all the electronic part is basically taking place in the strontium titanate. It also has the properties that it can be ferroelectric at low temperatures. And so what we have done is we've turned it around and tried to probe the properties of the ferroelectric properties or structural transitions in the strontium titanate using this related property of Etch-a-Sketch. So the second question is, well, maybe are there other systems that might be able to have more interesting or varied or even better properties? And I think that that people who have the tools, the theoretical tools, specifically to do simulations or not simulations, but calculations that rely on first principles of physics, may be able to do that. So we welcome those calculations.
Why was Einstein so upset with quantum mechanics?
Why was Einstein so upset with quantum mechanics? You know, I vacillate every morning. You know, should I be upset or not? Do I understand it? Don't I? I think it's a very there are some very strange predictions of quantum mechanics. That one, of course, is this indeterminacy. You know, God doesn't play dice. But the other one was this so-called EPR paradox, where you basically you have systems that are related to one another, that are entangled, that their fate, the measurement, fate, are related, even though they may be so far away that not even light or any other kind of information can transfer between them. These paradoxes have led to deep divisions within the physics community and have, in some cases, led to a re-examination and reinterpretation of what quantum mechanics really means. And so I think that it's still, I say that debate rages sort of below, people think about it maybe when they wake up in the morning, then they brush it off, and then they go and they do things with quantum mechanics. But it's something that we still worry about. Will we see a quantum computer within 10 years? My guess is probably not. We don't even have a quantum bit. So my definition of a quantum bit is like the transistor. You know, you have it. It's behind a glass case, and it's in a quantum superposition of 0 and 1, and it has a sign that says "Do not disturb," right? And it stays in that state indefinitely. We don't have anything close to that. What we have is something where we can initially put it in that state, and then that information, that quantum information, gets coupled to the rest of the universe on very short time scales. We don't have the ability to take advantage of it while that information is there and do the computations yet. I think it's going to require a lot more basic research. So we have sort of technological goals, but there's a lot of basic research that needs to be done. I mean, if we don't have a quantum bit, how are we going to make a quantum computer? So that there are a lot of approaches to doing this that involve very interesting fundamental physics.
Okay, great. So I think with that, with a sense of challenge and maybe a little hope, we'll thank Jeremy Levy again for a really
Welcome to the Aspen Center for Physics Public Lecture Series. The Aspen Center for Physics was founded in 1961 by local physicist George Stranahan with Michael Cohen and Bob Craig. The center provides a serene environment in which almost 1,000 prestigious physicists from around the world, young postdocs just out of graduate school to Nobel laureates, come together during winter and summer sessions to share, discuss, and initiate new research.
It took only 2 days at the center before I realized that this was what I had always dreamed doing science would be like. The beauty and peacefulness of the center is a really important asset to us. It is our opportunity to be cut off just enough from the daily grind to have lively discussions at the blackboards, share meals out on the lawn, gaze at the surrounding hills, and actually think about physics.
Thinking initiated at the Aspen Center for Physics, from biophysics to neutrinos to the outer reaches of the universe, has provided the underlying logic for the MRI, the CAT scan, and laptop computers, and will in the future provide the logic for innovations that will transform human endeavors.